Hello and welcome. We're going to be continuing on with electricity here. We're going to talk about what's called the electric field. Building on, we were talking about electrical forces last time. So this electric field, the concept was developed by a gentleman who did a lot of stuff with electricity named Michael Faraday. Michael Faraday is a British, well, he's a scientist. He didn't start out that way. He started out pretty impoverished. I think he's a bookbinder working in a little shop that was putting together books and everything, and so he got an opportunity to read a bunch of different books and was sort of fascinated by the science ones. Eventually he basically got a job being a valet, or like a servant essentially, for a pretty prominent chemist, and it was sort of to his benefit. The usually somebody in the chemist position and the sort of aristocracy and stuff wouldn't basically talk a lot with the hired help, but he was fairly friendly and nice with Michael Faraday. Sort of let him look through and read things and help him out with stuff that maybe other people wouldn't have. So he gained a lot more knowledge about science, about chemistry. Was very fascinated about it and went on then to become one of the great minds in chemistry and physics of the time. He eventually got older. But he did a lot of work with electricity, sort of some of the basic work, practical hands-on stuff. He basically had very little knowledge about math himself, but about a lot of how electricity and works and motors and generators and generating electricity and all that good stuff that people built on from there. But he also came up with this idea of the electric field. And the electric field is sort of a strange concept because it's something that doesn't actually exists. It's just talking about possibilities and potentials for what could happen in different circumstances. So it's just a region of space, what's going on around a charged object. If you just had a single charged object like a proton or an electron or just some charged metal ball or something and everything around it, what would it look like? What would it behave like? And basically nothing would be happening, but then if a positive charge or another charge in general were to enter that area, then that electric force that we've talked about would arise, things would get pushed and pulled, etc. So this would be talking basically just about what would be happening if something comes along, what would be ready to happen. So you'd be prepared then for when that other charge or charges arise, what would their general behavior be? The general equation for this electric field is going to look very similar to what we did with electric force. Our electric field, E, is Kc, Coulomb's constant, 8.99 times 10 to the ninth, the same one that we used before. Q is a charge, and then R is the distance from that charge. So the only difference here is that we only have one charge compared to when we did our electric force, we had two charges. So in general, and this is something that might be helpful when you get to an assignment later, if you do have, like let's say you've calculated out the electric field at a given point by maybe finding out the two or three different charges, what are the electric fields, and adding them together. And then there were a second part of that question asking you how do you find the electric force for that if a charge is placed at that spot. There's two ways to go about doing that. One would be to go and find the two or three different electric forces, sort of like we've done in the past, add them together based on whether they're going in the same direction or opposite directions and stuff. The much easier way to do that would be then to just take the electric field that you have already calculated and multiply it by that second charge, because that's all that's missing on this equation. So if you've already calculated out the electric field for the two or three charges, you can just multiply by that new charge, and that will be the electric force. That's sort of the short way of doing it. It might be helpful as you get to your assignment later. The direction of our electric field is going to be just sort of defined as that it always goes away from a positive charge and that it would always go toward a negative charge. So basically you're talking about, for the electric field, what direction would a positive charge, if you placed a positive charge into this area, what direction would it be getting pushed? So it would be going away from other positive charges, because they repel. It would be going toward any negative charges. So there's a little picture there. Going away from our positive charge on the left and going toward our negative charge there on the right. So let's take a look at an example here. If we want to figure out the electric field at the origin in this situation pictured here, so the origin being the center there, We've got two different charges, so much like when we were doing our electric forces, we'd want to take Q1 here, and you got its charge, which is 8 nanocoulombs, so that'd be 8 times 10 to the negative 9th. Nano is negative 9. And our distance would be the 16 meters, because this is 0 meters, this is 16 meters, so R would be 16 meters. And you can plug those in to that electric field equation that we saw a couple slides ago. Type those in, get a number. Do the same thing with Q2 here. You've got negative 6 nanocoulombs. You can just type in 6 times 10 to the negative 9th. Don't worry about the negative sign. Its radius is 9. Plug those in, get a number, and then contemplate, based on what we're just saying about directions, whether or not as this electric field passes through the origin here, as it's from this point, would it be going away from that point, so it would be going to the left, or would it be going through that point to the right as it goes through there? What direction would it be? And we'll see if we can add or subtract them. So you should really pause here, take a minute here to type it in, see what you get. Hopefully you get the same thing that I'll show on the screen here in some really bad handwriting in just a second. Okay, so I really hope that you have taken the time to type stuff in. If you didn't, then that's really foolish of you. If I'm looking at Q1 here, I'd plug in the 8 times 10 to the negative 9th, 8.999 times 10 to the 9th for the K coulombs constant, and then divide by 16 squared. If we do that correctly, we should get 0.28. But then I look at it, okay, I've got 1 sig fig, so it should be 0.3. This is really bad handwriting. The unit for our electric field, I haven't mentioned yet, is newtons per coulomb, N/C. That's N/C, as you can obviously tell. Our direction, that's always, I feel like, the trickiest part in this stuff. Okay, so this is a positive charge. Do electric fields go away from or toward positive charges? They would be going away from this positive charge. So as it goes away from this positive charge, it's heading to the left. As it hits the origin point, that line would be going away from our positive charge, so it would be going to the left. I'll just put an L there. For our second one, if we plug that in, then 6 times 10 to the negative 9th, 8.99 times 10 to the 9th, and divide by 9 squared, we'd be getting 0.67, I think, which would be, when we round it off to 1 sig fig, because we only have 1 sig fig, it would be 0.7 newtons per coulomb. And we got to figure out the direction again. So for this is a negative charge, our electric field goes toward a negative charge. So the electric field is going shoo, 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 and as it goes by that origin point, it'd be heading to the left as it goes toward our charge there. So it'll be going to the left as it goes to that point. They're both going to the left, so they'd be added together then. And we do 0.3 times 0.7 when you're adding our sig fig rules, that you do the same decimal point or place value, so it ended up being 1.0 newtons per coulomb. And then that would be going to the left. And I've decided to write out the full word left so that you have to suffer through this computerized handwriting. And there you go. And we'll put a box around it. Shoo, shoo, shoo. And that's our answer. 1.0 newtons per coulomb to the left. Okay. Electric field lines. If we want to draw some pictures of these, here's some different examples. You don't necessarily need to draw these down right now. We got them, but you can notice it's coming from our positive charges. All these arrows are going out away from our positive charge. They're all going in toward the negative charge. Another example, if we had 2 positive ones, all those lines are going out from both charges. If we have 2 negative ones, all those lines are going in from both charges. So some general rules that will be governing how we draw these electric field lines. There's 3 rules. Our first rule is that they start, any line's always going to start at a positive charge, or it'll start at infinity, so it'd either be starting at a positive charge or from the edge of your picture. Okay. The opposite, or I guess we could say the reverse of that would be that any lines are going to be ending at a negative charge or ending at infinity, if you reverse that around. Second rule, the number of lines leaving our positive charge or approaching our negative charge is proportional to the magnitude of the charge. So let's say if we had one of our two charges is twice as strong as the other charge, that charge then should have twice as many lines as the other one. So if one line had, or the weaker charge had 3, our stronger charge should have 6. If our weaker one had 5, our stronger one should have 10. So they just have to be in this correct ratio based on how strong their charge is. And we'll look at an example of that in a moment. And the last rule is that no two field lines can cross each other. They should always be separate. And you might have noticed in the other picture, none of them were ever crossing each other. They're always separate. Okay. So let's take a look at an example of that. Let's say here we've got a positive Q there on the left and a negative 2Q there on the right. So we got a 1:2 ratio. The one on the left is a charge of 1 relative, and then the one on the right is a charge of 2 relative. So we need twice as many lines here. So what we could do, we could do 1:2. Or we could do like jump up a little bit, 3, that's really bad, 3 again, to 6. We could do 4 to 8, etc. I'm gonna do, just to make it more interesting, I'm gonna do 5 to 10. Err on the side of maybe doing a little bit more lines, probably at least a minimum, I'd say, of 3 lines coming off any given charge, if not more, just as a general idea to give you a good picture. They should be symmetrical. I guess I hadn't mentioned that part, but you might have noticed in the other pictures they're always symmetrical. So I'd have 5 lines that are going to be originating off of this charge, and I'll have 10 lines that are going to be ending there. So we'll start with the 5 lines that are going to be starting here. If I want it to be symmetrical, maybe our first one just goes straight across here from one to the other. They always go from positive charges to negative charges, so my arrow will be going that way. If I want to space them out so that they're sort of symmetrical, another one coming here is going to sort of loop around and come back to this negative charge, and then another one over here. You could probably draw better on your paper than I can on the computer. One coming from over here is going to loop around and come in to our negative charge. That one's going to loop around through my 3:6 ratio up there that I don't need anymore, and then come over here. So I got 5 lines coming off of the red charge on the left. It's not quite as symmetrical as I would like. This one maybe should bend a little bit more so it matches that one. You get the idea, hopefully. This one needs 10 charges coming towards it because we need that 1:2 ratio. So the other 5 lines that are going to be coming to this negative charge, because they always end at negative charges, are going to be coming from infinity. So if I want to have it be symmetrical, I could have one coming in here and another one coming in roughly opposite it from the bottom. That's 2 more. One coming in from over here. One coming in from over here. And then our final one just coming straight in from the side, or as well as straight in as I can draw on a computer right here. And that would be our 10 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on here. 1, 2, 3, 4, 5. We got that 1:2 ratio. None of them are crossing. They all start at our positive charge or out at infinity, and they all end at our negative charge in this example. So that would be our drawing electric field lines. You can make some pretty pictures, sort of cool patterns, very nice and symmetrical. So give that a try, and then we'll see how things are going when I see you next time. Good luck.